Welcome back, everyone. Diving right in today. We're going deep on network protocols and I mean really getting into the guts of TCP/IP, how it stacks up against the OSI model, all that good stuff.
Yeah, think way beyond the textbook definitions here. We'll unpack the nuances, the history, even some of the bumps in the road these models have faced.
Perfect. So TCP/IP, it's king of the networking hill right now. Everyone knows that. But what got it there? Was it just good timing, or were there some smart design choices that gave it an edge?
Well, timing definitely played a part, right? TCP/IP, it matured way faster than OSI, and when the early internet really needed things to work together, boom, it was ready to go. But it's more than that. You see, TCP/IP, it was all about keeping it simple, keeping it practical. OSI, it aimed for like this perfect all-in-one solution. TCP/IP, it just wanted to get the internet talking.
So pragmatism over perfection, kind of.
Exactly. The early internet folks, they needed something that just worked and worked fast. Plus, TCP/IP, it treated each data packet on its own, made it super scalable. Internet could explode in size without getting bogged down in, complicated management.
Interesting. So even though it's crazy complex under the hood, at its core, TCP/IP is all about efficiency. But what about OSI? People love its structure, its comprehensive approach, but it ultimately lost out. What was it, just like too much, too clunky for the fast-paced world of networks back then?
It's true. The OSI model, impressive as it was, people saw it as this big, complex thing. 7 layers, yeah, that gave you a detailed view, but many thought, do we really need all that and all that complexity? It meant building and implementing OSI stuff. It took forever compared to TCP/IP.
So TCP/IP being lean and mean, that was its strength.
Yeah.
And kind of OSI's downfall all at once. But it wasn't just about how many layers, was it? I remember learning OSI was more theoretical and TCP/IP was all about, let's get this thing built. Did that factor in?
100%. OSI, it was like, here's this beautiful theory, now go make it real. Which is fine, but it meant those OSI protocols, they were slow to develop. By the time they were ready for the big leagues, TCP/IP was already running the show.
It's like they say, perfect is the enemy of good,
Yeah.
right? OSI was busy with the ideal solution. TCP/IP was busy connecting the world.
And that's the thing. TCP/IP, it was all about action. And that's what the early internet was all about. Experimenting, innovating, moving fast. Now, this isn't to say OSI was a failure. Not at all. It had a huge impact on networking, especially when it comes to standards.
True, true. Even though it's not the top dog in practice, OSI gave everyone a common language, a framework.
Speaking of frameworks, let's break down the layers of TCP/IP itself. How do they all work together to make data exchange seamless? And for those listening who've got the basics down, maybe you can shed some light on the lesser-known aspects or the challenges each layer faces. Love it. Let's start at the bottom, the physical layer. This is all about transmitting those ones and zeros, those bits, over some kind of medium. And yeah, it might seem simple, but we're talking signal loss, interference, meeting crazy high data rates for all those data-hungry apps. We're limited by physics here, whether it's copper wires, fiber optic, even wireless signals.
It's easy to forget, right? All those ones and zeros, they have to physically travel. Not so easy when you think about how far they go and all the different environments they travel through.
Exactly. So moving up, we've got the network access layer, sometimes called the data link layer. It manages the connection between a device and the network. The cool thing here is this layer deals with all sorts of network layouts. Simple bus networks, star configurations, ring configurations, you name it. Plus, it handles errors within a single network segment. Got to make sure that data is good before it even hits the internet layer.
It's like setting up a solid home base before heading out into the wild world of the internet, laying the groundwork.
You got it. Now, things get really interesting at the internet layer. This is where IP comes in, making sure data can hop across different networks no matter how they're physically set up. However, even IP has its challenges. We've got IP address shortages, especially with the older IPv4, and then there's NAT, Network Address Translation, trying to keep things afloat.
NAT, right. The behind-the-scenes hero, letting tons of devices on a local network share one public IP address. Super clever, but yeah, adds another layer of complexity to the whole thing.
It does. It shows you just how tricky it is to manage IP addresses, especially with billions of devices all wanting to connect. Okay, let's jump up to the transport layer. Here we find the heavy lifters of reliable data transfer, TCP and UDP.
TCP. That's one that makes sure everything arrives in one piece and in order, right?
Yeah.
Like a well-organized package delivery service.
That's it. TCP, or Transmission Control Protocol, makes sure your data arrives in order and error-free. Perfect for browsing the web, transferring files, that sort of thing. But all that reliability, it comes at a cost. A little bit of speed, a little bit of efficiency.
And that's where UBP comes in. for when speed is king, even if it means sacrificing a bit of reliability.
Right on. UDP, it's connectionless. No need to set up a dedicated connection before sending data. Faster, more efficient, but yeah, you might lose some data along the way. Think video streaming, online gaming, the occasional dropped packet isn't as noticeable as, say, a lag spike.
So it's all about trade-offs. Reliable TCP versus speedy UDP.
You got it. Which one you use, it all depends on what you're trying to do. Finally, we get to the application layer, the one we interact with the most. This is where HTTP, FTP, SMTP, they all hang out. Each one's got its own job. Web browsing, file transfers, email.
This is where it all comes together for the user, right? All those complex network operations, they get translated into something we can actually use.
Precisely. The application layer is the bridge between us and that intricate network. It shields us from all the data chaos happening below. Think of it like a fancy storefront. Behind the scenes, there's this intricate factory floor, but you just see the sleek, user-friendly facade.
Amazing how each layer of TCP/IP builds on the one before it. This intricate system that lets us do all this stuff online effortlessly. This layered design, though, it wasn't just someone's brilliant idea, was it? It took some inspiration from the OSI model.
Oh, absolutely. TCP/IP, it was all about practicality, but you can see OSI's influence in its structure.
Yep.
Which I think proves a point. Even though OSI isn't the king of the real world, it shaped the internet we know and love.
Great point. Shows you how connected ideas are. Even approaches that seem totally different, they can still learn from each other and make each other better. It really makes you appreciate the invisible forces behind every email, every video call. And speaking of complex systems, how about we unpack routing a little? Seems like that's where things get especially tricky.
Oh, routing. Yeah, that's where the real magic happens. Figuring out the best path for data to travel through a network, it's a beast of a problem. Think about it, right? The internet, it's like this massive web of networks, billions of devices, all sending data at once. Routers, they're the traffic cops making these instant decisions about where each little piece of data goes.
And those decisions, they're never easy, right? Network traffic jams, broken connections, new devices popping up. It's always changing.
Constantly. Routers, they've got these algorithms constantly talking to each other, figuring out the best path. Like Dijkstra's algorithm, that's a classic one, finds the shortest path between 2 points. But here's the kicker. Shortest doesn't always mean fastest, especially on the internet.
So it's not just about distance, it's about finding the route with the least resistance.
Exactly. That's where other algorithms come in, like Bellman-Ford. They factor in things like how much bandwidth is available, how much lag there is, even cost sometimes. Got to make sure data flows smoothly, even when things get messy.
Sounds like a constant balancing act. Finding that sweet spot as everything around it changes.
It is. And the internet, it's not getting any smaller, right? More devices, more data, those demands for instant video, lag-free gaming routing algorithms, they've got to keep up.
Right. It's not just finding a path, it's finding the best path and always adapting to what the network needs at that moment.
You got it. And that's where things get really neat, technically speaking. We start talking quality of service or QoS. It's basically giving priority to certain types of traffic, like your Zoom call. Way more important than someone downloading a huge file in the background.
Makes sense. Imagine your video call dropping out because someone's grabbing a massive file. That would be good.
Exactly. With 2OS, network admins can say, hey, this type of data, this user, even this specific content, it gets priority. Keeps things running smoothly, even when the network's under pressure.
The internet equivalent of a fast lane, making sure those important deliveries arrive on time.
Exactly. And this whole prioritization thing, it's going to get even more crucial with the Internet of Things, IoT, billions of devices, all needing to talk to each other.
IoT, yeah. Smart homes, whole smart cities, tons of data flying around. Amazing possibilities, but also a huge challenge for networking, right? How do we even begin to integrate billions of devices, especially when they might not have much power or bandwidth?
It's a big question, definitely. IoT, it might mean rethinking some of the basic rules of networking. Maybe we need more efficient protocols or even a whole new way of doing things, moving away from that classic client-server model.
So instead of every device calling back to some central server, they start talking to each other directly, sharing data, working together.
Exactly. Things like mesh networking, where devices relay data between each other. That'll be huge for IoT. Less reliance on one central hub creates a much more resilient network.
It's like shifting from a top-down structure to something more collaborative, more decentralized, which makes you think about security in a whole new light.
For sure. Billions of devices, all connected, each one's a potential weak point. Security becomes priority number one. We'll need stronger ways to verify who's who, better encryption, systems that can spot intruders instantly.
And all of this, it's built on those fundamental ideas we've been discussing, right? Network models, routing, balancing speed and reliability. It's fascinating how these core principles are being tested and reimagined in the face of new challenges.
It just goes to show you how powerful those foundational ideas were and how creative engineers and researchers are. They keep pushing the limits of what's possible.
We've gotten pretty deep into, the theory of it all, but let's bring this back down to earth for a minute. For anyone listening who's thinking, okay, but how does this actually work in the real world?
Yeah.
Can you give us some examples? Like, how are these concepts being used and challenged in tech today?
Absolutely. Take online gaming, right? Latency is everything there. A few milliseconds can mean winning or losing. So choosing the right way to send data becomes critical.
You're talking about TCP versus UDP again.
Yeah.
Reliability versus speed thing.
Exactly. In gaming, speed is king, which is why UDP often wins out. Yeah, you might lose some data packets here and there because there's no error checking or flow control, but it's way faster.
So drop packet every now and then, that's a small price to pay for a smooth gameplay.
Pretty much. And game devs, they're clever. They've figured out ways to work around UDP's flaws, like client-side prediction. Basically, the game on your end tries to guess what's going to happen next before even hearing back from the server. Helps hide that lag and keeps things feeling responsive.
So same protocol, different approaches based on what you need it to do. That's fascinating. Any other examples of how networking concepts are being pushed to the limit?
Oh, tons. Think about telehealth, right? Huge need for reliability and security there. Doctors are doing remote consultations, monitoring patients, even surgery, all thanks to good networking.
That's wild. But patient data, that's got to be top secret. What's being done about security in those cases?
Encryption is key. At multiple levels of the network model, data is scrambled before it even leaves your device, makes it near impossible to snoop on.
So it's like building a secure tunnel for the data, even if it's traveling over the public internet.
You got it. And this need for strong security, it's not just healthcare. It's everything now. Money, personal info, national security. It all depends on safe, reliable networks.
Makes you realize networking isn't just about computers talking to each other anymore. It's people, businesses, whole industries, all connected in ways we couldn't have imagined before.
And it's only going to get more interconnected. Smart cities, self-driving cars, virtual reality, all that relies on pushing the boundaries of what networks can do.
Exciting time to be working in this field, for sure. To be the ones building the future, basically.
100%. And it all goes back to what we've been talking about. Strong network models, smart routing, security, always security. These ideas, they're the foundation for whatever comes next.
Couldn't agree more. Well, I think that about wraps up our deep dive for today. And what a journey it's been. We've covered so much. Network protocols, the wild world of routing, even a glimpse into the future of networking. Hopefully, everyone listening has a better understanding of what makes the online world go round.
And more importantly, hopefully it makes you want to learn even more. Networking's a massive field, always changing. There's always something new to discover.
Absolutely. Thanks for joining us on this deep dive, everyone. Until next time.